Hi, everybody. My name's Nathaniel Stevens. I'm chairing this webinar. I'm presently the treasurer and chair-elect of the International Statistical Engineering Association. It's my pleasure to welcome a group of researchers from NASA. So first of all, Jonathan Rathsam is a senior research engineer at NASA's Langley Research Center. He currently serves as technical lead of survey design and analysis for NASA's Quests mission. He holds a PhD in engineering from the University of Nebraska, a BA in physics from Grinnell College in Iowa, and completed postdoctoral research in acoustics at Ben Gurion University in Israel. I'm sure I mispronounced that. Will Doebler is a research engineer in NASA Langley's Structural Acoustic Branch. He supports NASA's Commercial Supersonic Technology Project as a member of the Community Test Planning and Execution Team for the X-59 Quests mission. He has an MS in Acoustics from Penn State, a BA in Physics from Gustavus Adolphus College. And then finally, Nathan Cruze is a statistical engineer in the Engineering Integration Branch at NASA Langley Research Center, supporting the Quests mission full-time. He holds bachelor's degrees in economics and mathematics, master's degrees in economics and statistics, and a PhD in interdisciplinary programs, all from Ohio State University. So thank you guys for being with us today. We're all very excited for your talk, and feel free to get started whenever you're ready.
Wonderful. Nathaniel, thank you so much for that introduction. Again, my name is Jonathan Rathsam, and I'm the technical lead for survey design and analysis in NASA's Quests mission. My colleagues, Will Doebler, Nathan Cruze, and I all work at NASA's Langley Research Center in Hampton, Virginia. We're excited to share this presentation with you today, and thank you again to the International Statistical Engineering Association for this opportunity. Next slide, please. This webinar is organized into 3 parts. I'll begin by giving the context for NASA's Quests mission. Then Will Doebler will present a simulation experiment to illustrate how noise exposure in the Quests mission might vary across the nation. And finally, Nathan Cruze will speak about planning for community noise surveys, including dose response modeling and other practical challenges. Next slide, please. Supersonic flight has been around for 75 years. In the 1960s, supersonic commercial aircraft were proposed and several major community studies occurred. Supersonic aircraft were flown over communities and a social survey was conducted to learn how those communities responded to the sonic booms. The results of those tests showed that conventional sonic booms were just too loud to be acceptable. In 1973, commercial supersonic flight was banned over land. From 1976 to 2003, Concorde flew passengers supersonically over water, but had to slow down over land. And presently, NASA's Quests mission is building a low-noise supersonic experimental aircraft, the X-59, to enable survey data collection from the public on their reactions to these low-noise supersonic overflights. Next slide. So why is this research important now? My family and I live in Virginia, and my parents live 3,000 miles away in Oregon. Flying from coast to coast means a long day of travel. The goal of commercial supersonic flight is to get travelers to their destinations faster, so grandparents can spend more time with grandkids. There is an emerging potential market for commercial supersonic aircraft, and the evidence is multiple companies that are proposing commercial supersonic aircraft despite the lack of standards for supersonic overflight noise or landing and takeoff noise. NASA's vision is a future where air travel is broadly available to the traveling public. Future supersonic aircraft will fly over land without creating a so-called unacceptable situation, like the one from those community tests in the 1960s. The future supersonic aircraft will also be efficient and affordable and environmentally responsible, especially when compared with Concorde. The main barrier to this vision is the restriction on overland supersonic flight. National research agencies like NASA and policy agencies like the Federal Aviation Administration play a central role in developing the data that's needed for new regulations in order to enable this new market. Next slide. One key to overcoming the barrier is the development of appropriate noise level standards. The goal is to move away from the current speed limit, which prohibits any supersonic flight commercially, toward establishing an actual noise limit. A regulation with a noise limit requires data to inform it. And so the Quesst mission is intended to generate and provide that data to regulators for the development of that noise standard. Next slide. NASA's Quesst mission is a systematic testing approach. It culminates in the collection of public survey data on their reactions to low noise supersonic overflights. And it's divided into the 3 phases that you see here. Phase 1 is aircraft development. It's ongoing with Lockheed Martin in Palmdale, California, and it includes the design, fabrication, and ground testing of X-59. When ready, we'll conduct a series of so-called envelope expansion flights to prove that the airplane is ready and safe to fly outside of the test ranges in the National Airspace System. After that, we'll stay on the test ranges to conduct the acoustic validation, and that's what phase 2 is. Here we'll be proving that the acoustic signature of the airplane matches what we set out to design. We'll conduct detailed in-flight and ground measurements of the airplane signature in preparation for the community testing. And that's phase 3, the payoff of the mission. Phase 3 will be executed over 2 to 3 years, starting in 2024, and it'll consist of several tests over different communities across the US and possibly abroad. Next slide. The X-59 aircraft itself is driven by the idea of meeting a minimum set of requirements to accomplish the mission. The acoustic signal has to replicate a future larger aircraft. We have to be able to operate X-59 using normal flight maneuvers that would be expected for commercial supersonic aircraft. You can see in this slide some of the performance and geometry features. It's important to note that this is a new and unique airframe design in order to accomplish the signature shaping, but it does use many components from existing aircraft just to reduce the costs. It is a research aircraft, so the payload is just a single pilot plus some flight test instrumentation. Next slide. Here are some images of the airplane in fabrication. Some of the systems are being supplied by NASA, like the external vision system that enables forward vision without a forward-facing canopy window. The airplane is powered by an existing fighter aircraft engine, and the aircraft underwent some ground testing in Texas earlier this year in the springtime, and it's back in California now for the finishing touches. And the target first flight is within the next few months. So it's a really exciting time. Next slide. For context, in terms of sound levels, conventional sonic booms from Concorde and other aircraft that were used in those 1960s community tests, those were on the order of 105 decibels on this perceived level. So you can see in the red oval there, there's Concorde sonic boom. That's comparable to the sounds of thunder from nearby lightning or a car door slam from inside the car. And you know, it's noteworthy, these types of sounds can be very startling if you're not expecting them. By contrast, X-59's sonic thump is designed to be 75 decibels in green. So that's comparable to thunder from distant lightning or a car door slam heard from across the street. Next slide. So how big is the noise exposure region? As the aircraft flies supersonically, it drags this so-called carpet of sound behind it, like you saw in this animation. And that carpet can be 20 to 50 miles wide, depending on the altitude and the weather. So a 50-mile wide carpet across a flight path that's hundreds or thousands of miles long can encompass many millions of people in communities on the ground. And that's one reason why it's important to collect survey data from a large and geographically diverse population. Next slide. So in the 1960s, 2 major community overflight tests occurred. One was in St. Louis and another was in Oklahoma City. And each test lasted about 6 months. In St. Louis, there were 76 booms, and in Oklahoma City, there were upwards of 1,200 booms. And this figure shows the percentage of participants annoyed by various types of interference. Ultimately, the results from these studies showed that conventional sonic booms would not be acceptable. Sonic booms were just too loud at the sound levels that were comparable, as we said, to thunder from lightning nearby or a car door slam inside the car. One really important result from the community overflights was that indoor annoyance was the key driver of the non-acceptability. Next slide. So what is the evidence that X59's so-called sonic thump may be an acceptably low noise level? With indoor annoyance identified as the key concern, NASA has conducted laboratory tests, tests in small communities, and risk reduction tests in larger communities. And these tests each had increasing complexity, as you can imagine, and they show in general that the threshold of acceptable noise levels has been reached. And you'll see some of that data in a few slides. These earlier tests have prepared NASA to take the next step with flight tests over very large communities. In the interest of time, I'm going to skip the laboratory testing results and focus on the community tests only, but I am glad to share the references with on the lab studies with anyone who might be interested. Next slide. So our focus is conducting community overflight tests to create a dose-response relationship between the level of sound exposure and the community annoyance. In order to define an international standard, a large, diverse, and representative population has to be tested. The test has to be long enough to establish the effect of repeated exposure. And although we'd like to test in unlimited locations, we need to account for the fact that we do have an experimental airplane, an X-plane, with operational limitations. And those limitations drive our selection of airfields for use. Part of our planning efforts involve engaging the local community to create a trusting environment for the test. We plan a variety of public and STEM engagement opportunities as part of the overall approach. And even though our focus is on testing in the US, we know that international acceptance of the effort is important. So we're seeking to engage the international and regulatory community to ensure that the data will be acceptable. Next slide. NASA has been working to identify and minimize the risks that would be associated with community testing. A community test, of course, exposes an entire community to sounds while only surveying a sample of the residents on their perceptions. In 2018, NASA conducted a large community test using an F-18 research aircraft, performing a low boom supersonic dive, and that simulated the sounds of quiet supersonic overflight. In terms of community engagement, communications had to be tailored with many different audiences, such as elected officials at the local, state, and federal level. That began many months prior to the testing. Communications with residents who would be exposed to the sonic thumps. And those communications occurred via newspapers, press conferences, as well as via the local government and city hall. Communications had to be tailored toward mariners, people on the water who were exposed to higher level sonic booms just because of the dive maneuver that was being used. Communications with survey participants, communications with local students via the STEM engagement. In terms of flying the NASA research aircraft beyond the test range, a special air traffic control assigned airspace had to be prearranged and an environmental review had to be conducted. In terms of ground measurements of the acoustic signatures, 25 ground recording units were spread across a 60 square mile survey area, and those were linked via a cellular network to a host station. The field crew deployed and calibrated and retrieved these units daily. So that was a really large effort. In terms of the social survey, a web-based survey had to be developed. It had to pass governmental survey review, research ethics review, and the participants had to be recruited via postal mail and enrolled in the survey. One of the key lessons learned involved the need to automate and streamline the data analysis post-test in order to meet the swift cadence that's going to be needed for the X59 community tests. Most importantly, this large community test showed that NASA could successfully engage with a community in order to conduct the testing. And next, we'll take a look at the dose response results from this effort. This plot shows sample dose response curves resulting from two previous NASA community tests. The x-axis is the noise dose in terms of perceived level in decibels. That's the same scale that we saw a few slides ago with the Concorde and X59 levels. And then the y-axis shows the percent of highly annoyed responses. And the first thing to note is the high degree of scatter in the data, which is typical of social survey data. The second thing is that in both tests, 75 dB is associated with a very low percent highly annoyed. Now, as a matter of practicality, the sonic boom community tests have all been panel surveys. So a panel of participants respond multiple times. It just isn't practical to recruit a member of the public and then only request a single response, especially when these responses are needed promptly after each overflight. One consequence of having panel studies is the need for statistical models that account for the correlation among multiple observations from the same person. In a few moments, Nathan will speak more about the statistical models that are being considered for the community response data. But first, Will is going to present a simulation study. The study informs the experimental design of the Quesst Community Survey campaign. Specifically, the simulation investigated how X59's noise exposure may vary geographically across the nation, as well as across seasons. Will, the floor is yours.
All right, thanks, Jonathan. And first, I'd like to acknowledge Sarah Wilson and Alexandra Lebeau from NASA, as well as Vic Sparrow from Penn State, who did a lot of the heavy lifting for this study. And our reference is there below. It's going to appear soon in the Journal of Aircraft. Next, please, Nathan. First, we'll take a look at our goals of the simulation study. For this work, we set up a large-scale acoustic propagation simulation, and the goal of the simulation was to understand the X59's low boom loudness, the variability in the loudness, the exposure region size, and the variability in the exposure region size. The data from the simulation will aid in X59 community test planning and also make sure that X59's low boom would stay quiet in non-standard atmospheric conditions. The factors of interest driving the variability were climate, season, flight direction, time of day, location, and ground elevation. And most of these can be purposefully chosen when planning when, where, and how to fly the X59. Time of day was of interest to see if the atmosphere affects sonic boom loudness differently, for example, in the calmness of morning versus the more turbulent afternoon time. The flight directions also of interest, not because the aircraft is doing anything differently for a given flight direction, but because that direction of flight determines the sonic boom propagation direction relative to the prevailing winds. And some of our constraints were on computation time and meeting our project schedule goals, of course. And here we have the flow diagram of the basic simulation on the right. We provide our PC boom acoustic propagation model with information about the aircraft trajectory, the sound pressure near the aircraft, and then a large set of atmospheric profiles that include the pressure, temperature, winds, and humidity of the day, or of the timestamp. And then our output is our PC boom waveforms, their loudness, and also the size of the noise exposure region. Next slide, please. Next, we'll look at the design of experiments approach we use to select the resolution of the simulation study. So first, we needed to determine the locations at which to propagate the X59's low boom that would span the entire USA. We used a fast, flexible space filling design to choose locations at 2 different spatial resolutions. The green points there are a coarse resolution, and then the green and yellow points combined together are the fine resolution we looked at. Next slide. We didn't have the computational resources to conduct the analysis on the entire fine resolution, so we chose to first look at a subset in the Northeast US. The Northeast US was chosen because it will have some seasonal variability, and Pennsylvania is predicted to be one of the most heavily overflown states by supersonic aircraft due to its proximity to New York City, Boston, and Philadelphia, for example. We propagated the X-59 sonic boom through 5 years of atmospheric profiles collected 4 times per day and compared the coarse and the fine spatial resolutions. We also compared the results for 4 atmospheric profiles per day to 1 atmospheric profile per day. The resulting waveforms took up a substantial amount of storage space, which is one of our lessons learned for the full-scale simulation. Data management can be one of the more challenging aspects of large simulations. Next slide. To decide our resolution, a bootstrap forest analysis using decision trees was used. I'm going to build up one of the decision trees as an example. So after propagation of the X-59 sonic booms in that subset region, the first step of our decision tree, or maybe it's even step 0, is to pool all the data. So that's what's shown on the bottom figure here. The figure shows the carpet width, or the exposure region size, of all the simulated sonic boom carpets in that northeast subset. Each dot on the plot is the result of a single simulation run. Then the decision tree can split on values of the input factors to better explain the variability. Next slide. So for the first split, the decision tree shows the difference between the carpet width when the aircraft is flying west versus north, south, or east. It turns out that the prevailing winds in the US cause the west heading carpets to be narrower than the other directions. Next. So then each side of the decision tree is split again on other factors. The west heading was split on season, and the other heading group split on heading again. Each split explains more of the variability in the carpet width. Next. A final split is shown, further explaining the variability. Next slide. Okay, so that was for a single decision tree, but the bootstrap forest method is made up of 100 decision trees. Predictor screening was used to determine the most important factors impacting the carpet width, and the ranking of the factors is shown in the bar graph below. Again, heading is important for the carpet width due to the prevailing winds. Sorry, it looks like some of the text overran the figure there. All right, next slide. Okay, so predictor screening results for the fine and coarse resolution shown here for the mean perceived level, PL, that's the loudness, the range in perceived level, and the carpet width. One important outcome from the bootstrap forest analysis was that time of day was not an important factor in either resolution. Because of this, we chose to use 1 atmospheric profile per day instead of 4 to reduce our computational time. The predictor importance was also roughly the same for the fine and coarse spatial resolution, which was one clue that the coarse resolution will be adequate. But next I'm going to tease one visualization approach we use to illustrate this. Next, please. All right, so there's a lot going on this chart, so I'm just going to briefly tease some of these results and show that the results indicate visually that the coarse spatial resolution was adequate. What we have here So each of the dots on a given chart is one of our propagation locations. The dot color indicates the mean of the quantity of interest being plotted. In this case, we're showing the mean carpet width as the color. And then the dot size indicates the standard deviation of the quantity of interest. So a larger dot means a higher standard deviation of carpet width. We also split on the seasons, so the different columns in the chart show the seasons, and then the rows of the chart show the different aircraft headings. This is we like this style of plot because you can visualize many aspects of the data at once. And so if you look at like the east, the row for the east heading, you see that the mean carpet width is large, and that's because of the US's prevailing winds driving the carpet width higher. You can tell that by the dot color. Whereas the west heading, the bottom row, those carpets are smaller and they're a little bit less variable, which you can tell by the dot size. And the smoothly varying nature of the adjacent points indicates that either the spatial resolution was going to work for us because we are easily able to interpolate between the different points. All right, next slide. Here's our final simulation design. We used the coarse spatial resolution, which has 134 locations across the US. The X-59's low boom was propagated through 5 years of atmospheric profiles at each point, 1 per day, and at 4 aircraft headings. The results were generation of over 1 million sonic boom exposure region sizes and over 18 million low boom waveforms. To estimate the loudness, the variability, and the exposure region sizes away from the test points, multiple linear regression models were fit to the data using the same predictors as the bootstrap forest. And later on, when we show these results, we'll have about 50 kilometer spatial resolution. Next slide. Finally, I'll share some of the results and our other visualization approaches for the dataset. Our first technique we used were violin plots. So the plot on the right shows the loudness versus that off-track lateral distance from the aircraft. That's like to the side of the aircraft. And the violins are peak normalized probability density functions of sonic booms that arrive at each of the off-track locations, which we set to be about every 3 kilometers. The black line on the chart shows the X-59's loudness in a standard atmosphere, and then those dashed black lines show the median value of each of the violins. So most of the time, the X-59 sonic boom is quieter than the standard atmosphere, which is encouraging. And that standard atmosphere is the one that the X-59 aircraft itself was designed to. Next slide. We also used violin plots again to show trends across different climate zones. The map on the left shows the 7 climate zones in the contiguous US that are defined by the Department of Energy and its Building America Best Practices Guide. The violins represent the same peak normalized probability density functions, but this time instead of carpet width, we're showing the loudness, and the blue lines again show the median value of each of the violins. So typically we're seeing that the loudness is higher in the colder regions, and we also identified some seasonal patterns for the cold, very cold and marine group, the hot, dry, and the hot, humid group, and the mixed dry and the mixed humid group. They have similar seasonal trends. Next slide. All right, back to our dot plots here. We have geographical results for all of our generated data across the US for the perceived level. Again, the dot color describes that PL mean, and then the dot size represents the standard deviation of the perceived level. We tend to see loudness increasing in the north of the US and also in the more mountainous regions on in the Rocky Mountains, for example. And then you can see the dot size is increasing slightly in the south and especially towards the coasts. Next slide. For the previous chart, that was combining all the data from all the seasons and all the headings, but we can also split on season and heading, and that's what's shown here. So there's a lot going on this chart as well, but it allows you to, it helps you to decide when, where, and how to fly the X-59 during the community tests. So let's say we wanted our booms to be as quiet as possible during our testing. We might choose to fly over the southeastern US in the fall with the west heading. Although based on the size of the dots, we can expect our booms to be a bit more variable. That's an example of how this could be used to aid our planning. Next slide. Okay, now we're moving into the multiple linear regression results. So these allow us to predict the loudness and variability at locations that we did not include in our propagation simulation. So you just need to know the ground elevation, the lat and long, climate, the season, and the heading, and the model outputs the mean perceived level in this case. The contour maps, because they're at such fine spatial resolution, don't allow us to show more than one quantity at a time, so you don't see the standard deviation paired with the mean loudness in this type of chart, although models for those were generated. All right, next slide. Okay, I'll move into the summary. Our simulated data will be used to help decide when, where, and how to fly the X-59 in order to achieve our test goals. Our simulation resolution was decided by a design of experiments approach, and the results aid in the claim of national representativeness of the X-59 community test because we will sample areas with varying loudness across the country. Next slide. Okay, a little transition here. Our simulation experiment showed some potential geographic differences in our X-59 exposure loudness, which is one of the many reasons it's necessary to test at multiple sites. And so next I'll pass it off to Nathan Cruze, who will provide more details on the specific X-59 community response test survey administration, site selection, and our modeling approaches.
All right. Thank you, Will. Can you hear me?
Yep, got you.
Thank you. Yeah, as Will mentioned, there are, we have some evidence through the simulation study that even capturing objective measurements of noise exposure levels could differ by locality. So we also need to think about the impact on the perceptual experience, the social impact on different communities. As Jonathan mentioned, we have 3 phases. What I discussed will be focused on this 3rd phase in executing the community response testing. And to that end, I'll start with a demonstration of a candidate statistical analysis using past study data collected at Galveston in 2018. And then I'll conclude with some of the larger complex problems. And I think this is something that the Statistical Engineering Association can appreciate. I won't read them all off here, but collectively they speak to how we choose to administer our survey, to whom we administer, and really things even after the studies are conducted that can affect our ability to lay claim to national representativeness of the dose response curves that we produce. This is a pictorial synopsis of the data, the single event data that was collected at Galveston in 2018. Really, in the data set, we have close to 5,000 dose response pairs obtained from 371 unique individuals over the duration of testing. And what I can point you to that on that single event questionnaire, study participants were asked if they even heard the event, the sonic boom in question. And in about 56% of all those cases, they indicated they could not even hear it. So by assumption, they're lumped in with a not at all annoyed a perceptual response. The question or prompt that they were responding to basically asked, were you bothered, disturbed, or annoyed by the sonic boom? And for those that indicated that they could hear the event, they rated their experience on this 5-point verbal scale. There's a specific regulatory emphasis, essentially that bends or recodes this 5-point scale to define a binary variable. And in particular, the sum of the very annoyed and extremely annoyed are recoded as highly annoyed, and all others are assigned to not highly annoyed. But what I think I'd like to point out here is that you have just 47 of these highly annoyed responses out of nearly 5,000 data points. So this is a less than 1% event. The phenomenon, by the very design of our aircraft, the phenomenon we're trying to measure is a rare event. On the panel on the right here, you simply see the histogram of doses, noise exposure doses that were administered over the course of the Galveston study. And I'd say that this is roughly indicative of the range of doses that may be experienced during community testing. Certainly the range, if not the distribution at each test site. Continuing on, I'll share a little bit about past work that was done by Jasmine Lee, a talented master's student at North Carolina State under the direction of Dr. Allison Wilson. And so she did a Bayesian formulation of a random intercept logistic regression. This class of model kind of helps us account for the correlation of responses provided by the same individual. And in particular, in the Bayesian setting, we're specifying probabilistic relationships between the data generating process and model parameters, and then using Bayes' rule to obtain inferences on those model parameters. So if you have an index I over the 371 individuals, J denotes the specific booms to which they are each responding. H is our binary variable distributed according to a Bernoulli distribution, and that Pij is the probability of high annoyance. X here denotes the dose, and so what we're specifying is a relationship between the probability of annoyance to dose through this logistic regression. The first several lines of equations on the right describe the likelihood of the likelihood function of our data, and then the last three are a choice of non-informative prior distribution on our model parameters, namely normal distributions around the regression parameters beta naught and beta 1, and a vague inverse gamma prior on the variance of the random intercepts. Tabulated, you see the fixed effects and the standard deviation of the random intercepts. I attempted to reproduce Jasmine's work using the STAN programming language, and so this should agree fairly closely with what was in that JASA article. I'll also mention that the data are available with the JASA article, so it's possible to download these data and try it yourself. Really, what we're specifying in this process, though, is the conditional relationship or a subject-specific relationship. And so you have a family of individual dose-response curves. For our larger study aims, what we really need to get to is a population average or marginal dose-response relationship. And so, collectively, our survey team has given some thought to this problem. My colleague, Aaron Vaughn, has a Proceedings on Meetings of Acoustics paper comparing the Bayesian model to generalized estimating equations approaches that would take you directly to this marginal model. What we are kind of favoring at the moment is a marginalization across the distribution of random effects, kind of following the work of Pavlo 2015. And in a nutshell, you just integrate out the the normal distribution of random effects here using the plug-in estimates you obtained from the previous slide here. So here you're seeing the integration with respect to the normal distribution 0 and standard deviation of 2.62, and the resulting prediction curve in the graph on the right-hand side here. And so, as Jonathan mentioned, at 75 decibels, you have a very low probability or percent of the population that is highly annoyed. And even at the higher end of our test range, fairly low levels of annoyance throughout the population. No, I'd like to segue now into a discussion of some of the challenges or needs that we foresee in executing our intended study here. And I think I've structured these as kind of challenge and response to what we foresee. But one reality is that the experimental conditions are just going to change very quickly, sometimes within the half hour if our plane makes multiple passes per sortie. So we need to try and elicit prompt responses, especially to the single event survey. Jonathan alluded to some of the challenges that kind of drive us to recruit and retain a panel sample just because it's more practical than cross-sectional survey design. Some of this leads us to the importance of survey modes. And in this case, there's some discussion to be had because it doesn't just describe how study subjects participate, but even maybe who, because we're gravitating toward web-based or custom smartphone applications. Having that email address or internet access may be a barrier to participation. Some of the other modes we've considered, paper modes are just kind of not fit for our purpose. They won't meet the real-time needs. Even with some sort of telephone-assisted voice recording, you have low completion rates of your survey without callbacks. And so while we recognize that these internet and smartphone applications might circumscribe the pool of participants, we do have reason to believe that the phenomenon of high annoyance is not highly correlated with some of the factors that demographic factors that kind of prevent people from having internet access. It meets practical needs of the near real-time requirement, and in particular, our contractor team is developing a mapping interface that allows the user to indicate the location at a point in time. And so really there's a solution to a significant data linkage issue of the perceptual response to the dose through these modes. There's an added benefit that it simplifies non-response follow-up. Recruited participants at the very least have to have an email address to participate. Those that give permission to use their telephone number can receive text messaging reminders. And further, those who use the custom smartphone app may receive in-app reminders. We talk a little bit about site selection, and this is an important part of sampling. And as Jonathan mentioned, we have numerous operational constraints. So if we're thinking like statisticians and we know that there's a long list of potential airfields, well, great, let's just do a random sample of those. But wait a minute, we're constrained by cost and some of the study aims that require us to linger in place for about a month. In particular, there are really a limited number of airfields that can support the needs of the X-59 aircraft. And even among those, some feasible sites are actually rather close to each other. So you could go through the motions of, developing your short list, select 5 sites at random, but you may end up oversampling in very close proximity anyway. So really at this stage, we're proposing a purposive sampling. We have plans for 5 distinct test sites within the United States. Those decisions would be finalized in the future. But some of the challenges that go along with this are defining the orientation of the study region and the heading of the aircraft as it travels through it. We need to be able to commit to that for deploying ground recording systems, for example. Will alluded to some of the climate factors, and there's a sense in which when we go to the locality, we'll be dealing with the demographic composition that's already there. So to the extent that we want to oversample or capture minority opinion, it may be that we incorporate a higher than average national minority composition at the test site. Really, that decision is lumped in with the selection of the test location. It's kind of a common undergraduate statistics exercise when we discuss sampling to invite students to review a short problem or narrative and correctly identify the population of interest. And so we're going to go through that for ourselves on this slide. Namely, as Will mentioned, we have some predictive tools that help us describe the large study area where we can reliably produce and measure the sonic boom. And so that's kind of in the notional rectangle on the right. We'll be deploying a sparse network of ground recording units throughout this area. And the upshot is that we'll be estimating dose. And I'll say more on that on a subsequent slide here. But really, when it comes to the determination of our population, we're talking about this 600 square nautical mile region, smaller region within our study area. And so our population will be the general public, and in particular the adult population that we'll be surveying in this blue area depicted on the right. We can identify the composition of the population using census data, taking the census blocks and the union of census blocks in this blue rectangle. And really our sampling frame is going to be a list of postal addresses in these member census blocks. Once we commit to the study area, our sampling problem becomes a little bit more standard, more akin to household surveys or the recruitment of internet-based probability-based internet panels. We don't have a complete list of individuals, however, so we're going to have to specify the household as the variance unit, taking a systematic sample, for example, in a large sorted list of postal addresses. And then we need a method to get to the individual, to the person who will be filling out the sequence of surveys that we conduct. And so there's a method by Rizzo, Brick, and Park that helps us get, in addition to the household weight, the individual person weight. And so the upshot is that we will have a probability sample recruited specifically within this blue region, and we can make population inferences, for example, asking a question, did you hear the sonic boom? And we can get valid population inferences on the proportion of the adult population in blue that heard the event. I want to reiterate Jonathan's earlier point that all in the community are going to receive a dose or be exposed to these noise levels. But it's the nature of sampling that we're only going to speak to a few of them to get their perceptual responses. I think in the previous slide, you saw a cartoon and the placement of a sparse network of monitors throughout the region. And really what we'll have to do is estimate dose on a grid throughout this region. And so this, the means of estimating that dose is ongoing internally at NASA. Our colleague Jake Kloss has a publication available about one example. Some other options on the table include spatial Kalman filtering and other approaches. But I think it's important that we recognize the effects of having uncertainty in the dose levels. We can describe it as an attenuation of probabilities and a potential to overestimate or underestimate at certain places along the dose range. And in particular, the risk of underestimating may expose the general public to higher than ideal levels of noise. I'd say this is going to be a focus of our ongoing research. My colleague Will has a proceedings paper available on some Bayesian methods, and elsewhere in the acoustics literature, we have contacts that are focusing on this, taking methods from the applied statistics literature and trying to solve it in these community noise applications. Maybe one last thought here is the realization that we're going to have 5 kind of disjoint locations across the nation, and we still want to combine them in some meaningful way and lay claim to a dose response curve that is somehow nationally representative. I'll add that it's kind of a common aim of many acoustics papers to pool or do meta-analysis on many sources of noise for a variety of purposes. Maybe one of the most pertinent or comparable is the Neighborhood Environmental Survey that was recently conducted on behalf of the FAA. The emphasis there was on kind of takeoff and landing noise in close proximity to major airports in the United States, but nevertheless, what they showed was kind of an averaging of 20 locality population curves. As we think about this, I think it's important to recognize that we're still 2 years away from collecting live data at any of our prospective test sites. What we can say is that given the nature of our response, we have a categorical outcome and a known regulatory emphasis on the binary concept of highly annoyed. It's the nature of our survey design that we need methods that can account for repeated measurement, or the aspects of correlated responses coming from any one study individual. And we are aiming to produce a national marginal dose response relationship, combining up to 5 sites worth of data. One candidate available in the literature is the use of multi-level regression with post-stratification due to Gelman and Little in 1997. And just kind of in broad terms, you seek to divide the population into many categories. In particular, we're thinking about post-strata defined about certain demographic characteristics, if they are indeed related to or differ in degree of annoyance along those lines. And then essentially it reduces to an averaging of those dose response relationships within the post-strata. And so if we sample lower than national average among minorities or higher, we can weight appropriately to account for those and still try and lay claim to a nationally representative curve. I want to summarize the presentation, highlighting a few of the things that my colleagues raised. Jonathan shared some background on this Quesst mission and the ambition to make a noisemaker that's produced a phenomenon that has never quite been heard before, to measure it objectively, and then to measure the perceptual response through community testing and know that the result is fit for policymaking. Will, in his contributions to the peer-reviewed literature, pointed to some of the rationale for visiting multiple sites across the nation, and that the experience, the way it could be heard or perceived, can differ depending on location in the US, climate conditions, and other factors. And that points to the need to consider relevant statistical models that link this perceptual response to the objective measurement. And I think one of the things we'd like to continue in the Q&A is discussion about some of the decisions we've made, or things that this community can help us do to improve as we look to the execution phase. We'll make these slides available through ISEA. I would point out that a lot of our applied statistics work has been prepared for the Acoustical Society of America, or the Proceedings of Meetings on Acoustics. And I'll invite you to learn more about the Quesst mission at nasa.gov/Quesst. And with that, I think we're ready to invite everyone back on screen and do a little question and answer. So thank you all for your time.
Well, let me be the one to thank the 3 of you. That was a really great presentation. I've got lots of questions here from the audience. Many of them are saying what a great presentation that was. I don't know that we're going to have time to get to all of these questions. So I'm sorry if I don't get to your question. And if it's something that's pressing, I'm sure any of these 3 will be happy to take an email answer questions offline. So the first one, I guess, sorry to everyone asking questions. I got to pick and choose here. I'm going to ask a question. There's a few questions kind of about the Bayesian modeling that have come up. One, I guess, is sort of if you're going to make non-informative prior assumptions, what value is there in doing the Bayesian approach? What led to that choice? And then piggybacking off of that, just the logistic regression more generally can be very fussy if you've got imbalanced data, and you do, it seems, have imbalanced data. So I wonder if you've given thought to either of those things.
Yeah, Will and Jonathan, feel free to chime in. I think we will be, we're in the process of writing up some frequentist analysis of the same data set. And one of the things I will say about that, when you do these likelihood-based methods, there's kind of a fat integral that sits in that. So the frequentist methods use a variety of approximations to produce a numerical outcome, and sometimes those work better than others. In fact, this data set will break kind of Laplace approximation, and you could use packages like the G-Elmer function and the LME4 package to fit these logistic regression models and find a need to really ramp up the number of quadrature nodes to get the right approximation. So certainly that speaks to knowledge about the fussiness of the logistic regression, and also internally we're recognizing that what we are trying to measure is going to be a rare event. And so some of our contractor team is thinking about approaches about whether we need to include account for a preponderance who are never once annoyed during the study duration, for example. On the Bayesian side, we know that a choice of non-informative priors, you can often get results like the kind of frequentist or likelihood-based methods. I think we're building on the work of a graduate student in the Bayesian modeling, but in some ways, through that sampling rather than through the optimization in likelihood-based approaches, we were able to see a kind of a reasonable outcome from the get-go. You can experiment a little bit with the choice of priors, and you may see a little bit of sensitivity to the produced fixed effects. So I think that's worth saying. I think that's worth saying too in relation to approaches for dealing with measurement error. But we do see a lot of potential benefit for the Bayesian methods on the measurement error side too.
Great. Okay, I think maybe I'll ask one more question here, and this is maybe a higher level one. There's been a lot of other questions about the specifics of the statistics, but this is more like a higher order organizational one. It just seems like there's a lot of moving parts here and lots of different teams and stakeholders, and it just seems like it would be a lot to manage. And I'm wondering if you can kind of speak to that process and, I guess, maybe the trials and tribulations associated with it.
Jonathan, do you have any experiences as a contractor officer's representative on it?
Yeah, this is an astute observation that this project it involves multiple NASA centers. It involves our center in Virginia, but all of the flight testing, at least for phases 1 and 2, occurs at a sister center of ours, NASA Armstrong. We've got multiple partners. This contractor team that we've referenced, led by a company called HMMH. They're out of Boston. We also, we're working with the Volpe Center, which is a Department of Transportation. So definitely a lot of players, a lot of stakeholders. Eventually, this data is to be delivered to regulators. So the regulatory agencies are another stakeholder here. One of the best practices when handling multiple stakeholders is to engage early and engage often. And I'll give an example. I alluded to governmental review that's required for a survey of the public. And so that comes through the US government's Office of Management and Budget. They want to make sure that this data hasn't already been collected. We're not duplicating previous efforts, that it's that the public is informed about the time that's going to be involved with their participation. And NASA, when the communication between NASA and the Office of Management and Budget happens through one person in NASA headquarters. And so, one of my responsibilities is making sure that I know who's in that position and that they are informed, because that's a really critical piece in order for us to be able to conduct the survey, that we have that governmental approval. So staying in touch, making sure they're informed, and making sure I know if that person changes, which it has multiple times.
Yeah. All right. Well, thank you again for sharing this research and your experiences. It's a really interesting problem. And so I'm happy to have listened to it, and I'm excited for everyone else who either tuned in live or who may be watching a recording of this. So thank you to all of you for your attention.